Maybe is it useful to step back and talk about transform architecture in general?
Yeah, so maybe we should start with the GPT-2 architecture, the transformer that was derived from the Attention is All You Need paper. So the Attention is All You Need paper had a transformer architecture that had two parts, an encoder and a decoder. And GPT went just focusing in on the decoder part. It is essentially still a neural network, and it has this attention mechanism inside. And you predict one token at a time. You pass it through an embedding layer. There's the transformer block. The transformer block has attention modules and a fully connected layer. And there are some normalization layers in between, but it's essentially neural network layers with this attention mechanism. So coming from GPT-2, when we move on to GPT OSS, there is, for example, the mixture of experts layer. It's not invented by GPT OSS. It's a few years old, but it is essentially a tweak to make the model larger without consuming more compute in each forward pass. So there is this fully connected layer, and if listeners are familiar with multi-layer perceptrons, you can think of a mini multi-layer perceptron, a fully connected neural network layer inside the transformer. And it's very expensive because it's fully connected. If you have 1,000 inputs, 1,000 outputs, that's like 1 million connections. And it's a very expensive part in this transformer. And the idea is to kind of expand that into multiple feed-forward networks. So instead of having one, let's say you have 256, but it would make it way more expensive because now you have 256, but you don't use all of them at the same time. So you now have a router that says, okay, based on this input token, it would be useful to use this fully connected network. And in that context, it's called an expert. So a mixture of experts means you have multiple experts. And depending on what your input is, let's say it's more math heavy, it would use different experts compared to, let's say, translating input text from English to Spanish. It would maybe consult different experts. It's not quite clear, not as clear cut to say, okay, this is only an expert for math and for Spanish is a bit more fuzzy. But the idea is essentially that you pack more knowledge into the network, but not all the knowledge is used all the time.
Mm-hmm.
That would be very wasteful. So you're kind of like, during the token generation, you're more selective. There's a router that selects which tokens should go to which expert. It's more complexity. It's harder to train. There's a lot of, that can go wrong, like collapse and everything. So I think that's why Olmo 3 still uses dense. You have, I think, Olmo models with mixture of experts, but dense models, where dense means so also it's jargon. There's a distinction between dense and sparse. So mixture of experts is considered sparse because we have a lot of experts, but only few of them are active. So that's called sparse. And then dense would be the opposite, where you only have like one fully connected module and it's always, utilized.
So maybe this is a good place to also talk about KV cache, but actually before that, even zooming out, like fundamentally, how many new ideas have been implemented from GPT-2 to today? Like how different really are these architectures?
Picture like the mixture of experts. The attention mechanism in GPT OSS, that would be the group query attention mechanism. So it's a slight tweak from multi-head attention to group query attention. So there we have two. I think they replaced layer norm by RMS norm, but it's just like a different normalization layer. Not a big change. It's just like a tweak. The nonlinear activation function, people familiar with deep neural networks, it's the same as changing sigmoid with ReLU. It's not changing the network fundamentally. It's just like a tweak, like a little tweak. And that's about it, I would say. It's not really fundamentally that different. It's still the same architecture. So you can convert you can go from one into the other by just adding these changes, basically.
It fundamentally is still the same architecture.
Yeah. So, for example, you mentioned my book earlier. That's a GPT-2 model in the book because it's simple and it's very small. So 120 million parameters approximately. But in the bonus materials, I do have Olmo 3 from scratch, Gemma 3 from scratch, and other types of from scratch models. And I always started with my GPT-2 model and just, tweaked added different components, and you get from one to the other. It's kind of like a lineage in a sense. Yeah.
Can you build up an intuition for people? Because sort of when you zoom out, you look at it, there's so much rapid advancement in the AI world. And at the same time, fundamentally, the architectures have not changed. So where is all the turbulence, the turmoil of the advancement happening? Where's the gains to be had?
So there are the different stages where you develop the network or train the network. You have the pre-training. Now, back then it was just pre-training with GPT-2. Now you have pre-training, mid-training, and post-training. So I think right now we are in the post-training focus stage. I mean, pre-training still gives you advantages if you scale it up to better, higher quality data. But then we have capability unlocks that were not there with GPT-2. For example, ChatGPT, it is basically a GPT-3 model, and GPT-3 is the same as GPT-2 in terms of architecture. What was new was adding the supervised fine-tuning and the reinforcement learning with human feedback. So it's more on the algorithmic side rather than the architecture.
I would say that the systems also change a lot. I think if you listen to NVIDIA's announcements, they talk about these things like, you now do FP8, you can now do FP4, and what is happening is these labs are figuring out how to utilize more compute to put it into one model, which lets them train faster, and that lets them put more data in, and then you can find better configurations faster by doing this. So you can look at like essentially the tokens per second per GPU is a metric that you look at when you're doing large scale training, and you can go from like 10K to 13K by turning on FP8 training, which means you're using less memory per parameter in the model. And by saving less information, you do less communication, you can train faster. So all of these like system things underpin way faster experimentation on data and algorithms. That is kind of like, it's this kind of loop that keeps going, where it's kind of hard to describe when you look at the architecture and they're exactly the same, but the code base used to train these models is going to be vastly different.
Mm-hmm.
And you could probably, the GPUs are different, but you probably train GPT-OSS 20B way faster in wall clock time than GPT-2 was trained at the time.
Yeah, like you said, they had, for example, in the mixture of experts, this FP4 optimization, for example, where you get more throughput. But I do think this is, for the speed, this is true, but it doesn't give the model new capabilities in a sense. It's just how much can we make the computation coarser without suffering in terms of model performance degradation. But I do think, there are alternatives popping up to the transformer. There's text diffusion models, completely different paradigm. And there's also, although text diffusion models might use transformer architectures, but it's not an auto-regressive transformer. And also Mamba models, it's a state space model, but they do have trade-offs. And what's right is there's nothing that has replaced the auto-regressive transformer as state-of-the-art model. So like for state-of-the-art, you would still go with that thing. But there are now alternatives for the cheaper and like alternatives that are kind of making compromises, but it's not just one architecture anymore. There are little ones coming up, but if we talk about the state-of-the-art, it's pretty much still the transformer architecture, autoregressive, derived from GPT-2 essentially.